So now we have, by Rayleigh's theorem, by Rayleigh's theorem applied to H, right? Then we have that that H is equal to 0. The derivative of H is equal to 0 for some x where x is strictly between a and b. Right? This is Rayleigh's theorem. This because this function h has the same value at a as at b. Right? Now, what is the derivative of h? Yeah. So the derivative of h is the derivative of f. And this is just, again, this is just a constant. So we have to keep that minus f of b minus f of a, b minus a. And then the derivative, so this is just a constant, and then derivative of this is just 1. So this here is what the derivative is. And so you see that, so we have this x where the derivative is 0, so this here is 0. But if this here is 0, it means that this thing here is equal to that, right? And so that was the mean value theorem. So this proved the mean value theorem. Okay. There's a second mean value theorem, and the second one is the Cauchy mean value theorem. And so this is a little more fancy. So the Cauchy mean value theorem So this is the following, that you have two functions, f and g. So you have f and g on some interval from a to b into r, and they are both differentiable. They're both differentiable, and then the claim is that there exist x. Let's call it x0. Maybe I should have called it x0 up there. It's just one. There exists x0 with x0 strictly between a and b. And okay, and so that it's something about that the derivative of the both functions kind of behave like the mean value theorem at the same time. Okay, so it is that the derivative, I will explain this in a second, that the derivative at this point times g of b minus g of a is equal to the derivative of g at x0, f of b minus f of a. Okay. So this is the Cauchy mean value theorem. Okay. So let's say that for this here. And let's just look at that expression here before we prove it. The Cauchy mean value theorem. So if you had, if now, so as a consequence, so observe that if g of b is not equal to g of a, and g prime at x0 is not equal to 0, if you have that, then you could divide. You could have this expression that say that then you would, by just dividing this here on both sides and this here on both sides, you would get that f prime of x0 divided by g prime at x0 is equal to f of b minus f of a, g of b minus g of a. Okay, you would have that, right? Now, I could think about this thing here as f of b minus f of a divided by b minus a. So I could think about it like this, and then times b minus a is g of b minus g of a. Okay, and so you see that this here, it's something about, right? The actual mean value theorem say that this thing here, that there would be some point x0 in between that was equal to this, right? That would be the mean value theorem applied to f, right? And the mean value theorem applied to g would be that there exists some x0 so that 1 over this is equal to this thing here, right? And the Cauchy mean value theorem say that you can kind of arrange so that both of these things happen at the same time. Okay? So this seems actually pretty good, right? I mean, you can do it at the same time. It's a little bit surprising in a way. But the proof is quite trivial. But it's useful. So the proof is the following. That you just look, right, so this is what we want to prove, right? So you just define, and the x0 is unknown. So if I take this expression that I want to prove, if I move this thing here over on the other side, right? Then I would get, so I would define, in this case, I would define f of h of x to be f of x g b minus g a minus g of x f b minus f a. So I would define it like this, and you see that when you now take the derivative of h, you just get this here. Right, this is because everything else is constant. So this is what you get, right? And you want to find a x0 where you want to find x0 where this thing here is 0. Right? To find such a x0 is the same as saying that you have find an x0 over here, right? Now, so now let's see, what is the value of h at a? If you plug in a here, then you get f of a, g of b minus g of a, minus g of a, f of b minus f of a. Okay? And so now you see that's here I have I have this one here, this one here. I have f of a times g of a. That comes with a minus sign. I have the same term over here, but that comes with a plus. So those two cancel out. So I'm just get f of a, g of b, minus g of a, f of b. So that's what I get there. And now I look at h of b. So if I plug in b up here for x, then I'm getting then I get f of b, g of b minus g of a minus g of b, f of b minus f of a. Okay? And now you see that this, when you multiply this by this, that term, f of b, g of b, you have this over here also, but it comes with a minus sign, so those cancel out. And so you're getting a term, the only term that lives is this one times that, so minus g of a, f of b, and then you get this term minus minus or plus g of b, f of a. And right, that's right, sorry. And now you see that this is the same as that, and these two here are the same, right? So you see that, so we conclude here from this, we conclude that h of a is equal to h of b, right? So again, it's satisfying the requirement of Rolle's theorem, and so there is this intermediate point where the derivative is 0, but if the derivative of h is 0, that's exactly the point we wanted to find, right, where you have this, right? Okay. And so again, you know, the Cauchy mean value theorem is sort of a stronger statement, but it's a stronger statement because it's like it allows you to have two functions, and then you know this point where sort of to some extent the mean value for both functions are satisfied, right? That's the idea. But it's an example of where actually the proof, it in fact worked more generally than what you used it for initially. And initially you just use it for a single function, right, to prove the mean value theorem. Okay. Now, so now we want to prove. So now we have a number of consequences of this, and the first one. Let me start. Let me start with another consequence of Rolle's theorem, and then I'll come back to the Cauchy mean value. So Taylor expansion. So the idea here is that you have a function f, and you have a function. Let's say that it's a function on R, doesn't need to be defined on all of R, into R, and f, I'm assuming, so let me do a special case of this. So a special case first. So I assume I have a function like this, and that is differentiable. And then I'm assuming that the derivative, so the derivative is now a function from R into R. And I'm assuming that the derivative is also differentiable. And the idea is now that I'm looking at the function, and the idea is like this. Again, in a minute I'll prove a more general statement, but I just prove this one first to make the idea clear. So the idea is that you want to say that f locally can be approximated by a polynomial. So that's the idea of the Taylor expansion. Okay, that if you take a function, if you take a function like this, some function, and you take a point, then in a neighborhood, let's say that this is some point here, x0, then in a neighborhood of this point, instead of looking at the function, you could get a very good idea about how the function behave in this small neighborhood if you look at a certain polynomial. Okay, and the higher degree the polynomial, the better the approximation is to the function. And so we'll just do a simple version of this first, where you're looking at the, so in this case I would look at the, so I have, so we have f here, and I'm interested in f. So we will be interested in f near x0, and then you're looking at what's called the Taylor polynomial at x0. Okay, and the Taylor polynomial, it depends on how many times you're willing to take the derivative. And so in this case, I just look at the first Taylor polynomial. So this here is, and now it is a Taylor polynomial at x0. So this thing here is, by definition, the value of f at x0 plus, and then the derivative of f at x0, x minus x0. So this here is the first order Taylor expansion. So it's this here is often called the first order Taylor expansion at x0. Okay. Now, what you're interested in is you're interested in showing that this polynomial here. So again the idea is that that f of x should be almost equal to p1 of x if x here. Sorry, if x is almost equal to x0, right? So near x0, the function is very well approximated by, in this case, this linear function, okay? And so now, but you want to, so now the key here is what is, how do you estimate how well it approximates, okay? And so the thing is that so the statement is then that, so you have here x0, you have here x, and the claim is now that there exists some c between x0 and x, so strictly between, so between, which means that it's strictly between. Let me just write that in. X could also lie on the other side, right? Then it's sort of obvious what I mean strictly between also. So there exists some x, some c in between these two, so that f of x is equal to this Taylor polynomial plus, and then the second derivative. So this is the derivative of the derivative. This is so f2 here is the derivative, and then you take the derivative, like that. And that is evaluated at c, and then divided by 2, and then it's x minus x0 square. Okay. And in a minute, I will just do the general case of it. Okay, so this is the right. And so now, how do you prove this? So what you do is that, so let's try to prove this. So I define a m. We define a m. M is just some real number. And it's defined so that f of x, I wonder if I should, in my notes here, I call it, just because I thought it was clear, and maybe I will do this here also, I'll call this point here A, and this here B. And then C here is somewhere in between, right? So this means that this thing here is B, and this here is B, and this here is then B, and this here is A. Okay, it's just to be clear that somehow, you know, you're kind of fixing X, right? Okay. Now, so to prove it, so we look at this thing here, and you look at this thing here, and you define, and we subtract P1 of B, and then we define M so that you have that this thing here is B minus A square, right? So define M by this thing here, right? This here just gives you some number. A and B are different, so this is non-zero. So this here, so M is just given by, that is this difference here, divided by this here, times 2, right? So that's how we defined M. But now we want to show, right? So like M is like, if you do it like this, it's like M is okay. It's just by definition, you have. So now we have, right? So we have by definition we have that f of b again is equal to p1 of b plus m2 b minus a squared. Okay. But we need to prove we need to show that m here is the second derivative of the original function at some intermediate point, right? That's what we need to prove, right? And so you're looking at so now we're looking at the function h of x equal to f of x minus p1 of x minus m over 2 x minus a squared. Right. So if we're looking at this function, well, if we're looking at h of, let me do b first. So if I do b, then this here is f of b minus p1 of b minus m over 2 b minus a squared. But m was defined so that this thing here is equal to that. So by definition, this is by definition of m. I have that this thing here is 0. Right. If I'm now looking at h of a, well, this thing here you get f of a. Here you get minus p1 of a. If you plug in a here, then this is 0. So this is what you get. Right? But remember how p1 was given. P1 was here, right? And we now do it at a. So this here is really a. Okay? So you see that when you plug in x here, this thing here is 0. So you just get f of a here. So this thing here is f of a minus f of a. So that's 0. Right? So you see that if you're looking at this function here, then at a it's 0, at b it's 0. So by Rolle's theorem, there exists C1 with between A and B such that h prime of C is equal to 0. Okay? Now, sorry, this is the C1, right? It's not the C we're looking for, right? The C we're looking for is something where the second derivative is something, right? But now you see that now you have this function h, and here you have A, here you have C1, and then you have B is further away, like this. And you have that the derivative, in this case the derivative is 0 at A, and the derivative, not at A, but the derivative at this point here, h prime, is equal to 0. Let's calculate what the derivative of h is at A. Right? I want to apply the Rolle's theorem a second time, but in order to apply Rolle's theorem a second time, I really need the derivative of h at A to be 0. But let's see what it's equal to. And so again, we have h up there at the top. And so this means that h prime is equal to f prime minus, and then the Taylor polynomial, here was the Taylor polynomial. This is just, when you take derivative, this is just a constant. You're getting f prime a, right? This is all it gives you when you take the derivative of this here. And then you're getting minus, and you're getting m x minus a. That's when you take the derivative of the last term. Okay? So this is what you get, and this here is at x. But so now h prime at a, this is f prime at a minus f prime at a. This thing here is actually 0. So you see that this whole thing is 0. Right, so we have, what we have is that we have that h prime at C1 is 0, and this is also equal to the derivative of a. Right? So we can apply Euler's theorem a second time, right? So by applying Euler's theorem, a second time, we have a C2. And now this C2, that's really going to be our C in this case. So we have a second C where the derivative of the derivative, so the second derivative of h at that point is equal to 0. Okay? And this one here, remember this here is when you apply Euler's theorem, you started with A, you had here B, then you got C1 that was between these two, that was C1, but now you're looking at H prime in this interval, and so the second one is lying here, right? So it's certainly between A and B, but it's actually even between A and C1, right? Now, what does this here mean? Right. So we hope that this is the point we're looking for. And so to calculate the second derivative, so this here was the derivative of h. So we just need to take another derivative of h. So if we do this, then we get that, so h double prime of x at some x is equal to f double prime at x. And then you see this thing here, this is just a constant. This is a linear function, so the derivative of this one here is 1. So you're getting this minus m. Right, and now we know that h double prime at this intermediate point, C2, which we also call C, that's equal to 0. So this means that f double prime at the C minus m is equal to 0. So this means that m really was the second derivative of f at this point. Right? Okay, so you see this proof is sort of clever that but if the proof seems very clever, but if you think about it, I mean, it's applying Euler's theorem twice, but it's sort of in a way the only thing it could be. But anyway, okay. So that was Taylor. This was just a special case of Taylor expansion. Let me state the general case. So the general case is to proving the special case, we applied Euler's theorem twice. But you can actually apply Euler's theorem like k times. And so if you apply it k times, then you're getting the k-Taylor expansion. So this here is the general case of the Taylor expansion. So general case. Of Taylor expansion. So the general case is that you take a function on R into R. You assume that f is differentiable, but also that f prime is differentiable, and all the way up to, say, f, right, you assume that it's differentiable, and all the way up to the k minus 1 derivative is also differentiable, so this here exists. Right, so all of these exist, all these derivatives exist. And then the claim is that, so now the Taylor polynomial, the k Taylor polynomial, or or sometimes called the Taylor polynomial. Of degree k minus 1 is that you're looking at, so this, this should be the k minus 1 Taylor polynomial. So this is where you write, so you take, again, you have here A and you have B. Let me write it with A and B instead of with X, because I think it's a little clearer. So the thing is that the polynomial is where you say you expand around A, and so the polynomial, this is the k minus 1 polynomial. For that we write it in terms of X, and this is the polynomial where the constant term is the value of f at A. The derivative, the coefficient to the first order term is f prime at A, and then x minus A. The coefficient to the second is the second derivative at A, and now it's divided by 2 x minus A squared. And then it's this next one is f triple prime. And now it's really 3 times 2 times 1 times x minus A to the power 3. And then you continue like this up to the k minus 1 derivative, and then it's k minus 1 factorial x minus A, k minus 1. So this is the k minus 1 Taylor polynomial. Okay, and so you observe that you can just write it. So it's typically written like this, that f, the I derivative in A divided by I factorial x minus A to the power I, and I is now summing from 0 to k minus 1. This is by definition equal to that. Okay, so that's the Taylor polynomial, the k minus 1 Taylor polynomial. And now the general case of the Taylor expansion is then, so the general case of the Taylor expansion is then that so this is like the theorem, Taylor expansion. So you have again this function on R into R, and you have that all of the derivative up to and including the k derivative, they all exist. And then you have that f of b is equal to the k minus 1 Taylor polynomial at b plus, and then this term is usually called the remainder term. And the key point here is that it's easy to estimate the remainder term because there's an expression for it. This is the k derivative of f in this point that is an intermediate point divided by k factorial c minus b minus a to the power k. Right, and where c here is lying between a and b. Okay. Right, and again, the idea is that you take you have a function, any function. It needs to be differentiable k times, but then actually it's very close to a polynomial of degree k minus 1, and you can estimate it, how close it is in terms of this term here. Okay. And so the proof of this, right, so the proof is really just what we did, but let's just go over it again. You know, we only did the first where we did it in the case where k was equal to 2. And now let me try to do this in general. So you're looking at f of b minus, right, we have this Taylor polynomial, k minus 1 Taylor polynomial. And you're looking at, you define m by the equation that this here is m over k factorial times b minus a to the power k. So this here is how, right, m is defined, right? B is not equal to m, so this is just some positive, some whatever, some, yeah, it's actually a positive constant, right? And so you can just, right, so you can just, m here is given as the difference of those two, and then divided by this and multiplied by k factorial, right? So this defined m. And so, and now what you do is you then define h as before, or similarly to before. H is then going to be f of x minus p k minus 1 of x minus m over k factorial x minus a to the power k. Right, that's how you define h, right? And by definition of m, by definition of m, you have that h of b is equal to 0, right? This is another way of saying how we defined m, right? Now, if you look at, so now h of a, well, h of a here is, h of a is just f of a minus p k minus 1 of a minus m over k factorial x minus a to the power k. And this is, for a. So this one here is clearly 0. A minus a is 0, right? So that's clearly 0. And this thing here, that's this polynomial, I wrote it up here, right? So if you plug in here a, you see this term here, and all the other terms drops out. It's only this one that lives, right? So this thing here is, this is the same as f of a. And so you have that the whole thing is actually 0, right? So because we chose m this way, we see that now Rayleigh's theorem can get started, right? And so Rayleigh's theorem can get started, and this means that there exists a C1 between a and b where the derivative of h is 0, right? Now you check that if you're looking at this function again, and take the derivative at a, the derivative at a is also 0, right? In fact, the whole idea is that all these derivatives up to the k minus 1 derivative of, if you're looking at the k minus 1 all the way up to the k minus 1 derivative of h, they are all 0 at a. Okay, so you can repeat the Rayleigh's theorem. So this first here, this thing here, together with this, allows you to find this C1 strictly between A and B, where the derivative is 0, then you observe that the derivative of h at A is 0. This then allows you to find a point between A and second point, C1, which was less than B, where the derivative, second derivative, is 0. Now you use that the second derivative of h at A is also 0. So this gives you apply Rother's theorem one more time. Each time you apply Rother's theorem, the C's is moving to the left, right, towards A, right? And so you apply it, you apply Rother's theorem k times, and once you do this, you get eventually that this m here is the derivative of the original function at this point. Okay. So I wrote this out. Now I did the special case, and I try to explain this here. I wrote it out in the notes. It's written out in the general case only, but on the other hand, it's written out completely there. Any questions? There's two things we didn't get to. There's these two rules about how to evaluate fractions. That uses the Cauchy mean value theorem, and I'll start with those. They're in the notes, but I would start with that next time. Yeah. You do up to k derivative. It's when you do the k derivative, then you get that's when you get the C that you're actually looking for, right? And so in the special case, I looked at k was equal to 2, and the Taylor expansion was a linear, so it was a polynomial of degree 1, so k minus 1 was 1, right? And so in the special case, we applied Rother's theorem twice, and in this case, we do it k times.